Okay, so shall I begin?
Mm.
Yes, okay. It's my pleasure to introduce Professor Iida for his keynote talk today. Professor Iida is the Vice President of the Japan Advanced Institute of Science and Technology, where he also leads the research unit for computer and games. Professor Iida is known for his skill and his contribution to shogi and computer shogi. He's a seven-dan professional shogi player. Meanwhile, his team's shogi program Tacos is a four-time computer Olympiad champion. Tacos has also played on par with a professional five-dan player and was said to be the reason why AI tournaments between professional players and programs are strictly regulated now in Japan. Professor Iida is also known for his expertise in game and AI research. His work on game refinement theory and entertainment technology goes back almost 2 decades. He is also a valuable member of our community, serving for many years as the Secretary Treasurer for the ICGA. We've invited him today to give a talk on recent developments in game refinement theory. My understanding is that his team contextualized several games in the framework of physical laws of motion, and this analysis helps us understand how and why we enjoy these games. This is a fascinating topic that goes beyond creating agents that play a game strongly. In fact, it strikes at the very basis of game design, which is incredibly interesting. So without further delay, let's welcome Professor Iida.
Is not?
Yes, we can see it. We can hear you.
It is not full screen, huh?
Yes, it's not in presentation mode.
Should be the full screen, huh? What is a full screen? Here. Maybe this one. I'm not sure how we can do this full screen.
Is there like a present somewhere, maybe?
Huh?
This is PowerPoint, right? So I would probably download it and then use presentation mode.
Is it okay now?
It is okay.
We can see it. Yes.
Okay.
Yes.
Thank you. So,
Thank you.
hi, everyone. I'm Hiroyuki Iida from JIST, Japan Advanced Institute of Science and Technology. Thank you for inviting me to be a keynote. I'm happy to be here as part of this prestigious conference, ACG, Advancing in Computer Games Conference. Today, I'd like to share my recent research topic, which I call Motion in Mind, based on the concept of gravity in mind. So since my PhD year, I enjoyed so much my research life. Special thanks to Professor Yoshiyuki Kotani and Professor Yafan Herik. With their kind supervision, I completed my PhD in 1994 with focus on the opponent model search. My first job opportunity as AI researcher as postdoc was ETL, Japanese Government Research Institute, working together with my boss, Dr. Hitoshi Matsubara. Dr. Matsubara, I took a pleasure to start computer game research community in Japan. For example, GPW series, which is still running game program workshop, was one of such highlight platform to accommodate game and AI researchers in Japan. So let me see. Having spent some, I would say, 30 years as AI researcher and previously another 30 years as Shogi 7-dan Grandmaster, as shown in this photo. It's photo actually from some 40 years ago. What would be my conclusion or even important findings? My intuition through Shogi player experience, we start a game as athlete to win the game, but end as artist That's my intuition. Why a game player needs to be an artist? If a players miss the best timing of the resignation, the game would be boring or lose its attractiveness. How can players determine such a best or even appropriate timing of resignation? What is the evidence of such a good practice? How can people or even AI understand such resignation mechanism? Indeed, here is one of the titles composed by Shakespeare, All is Well, that ends well. We call it zanshin in Japanese as a state of mind to express such a concept. In China, more than 2,000 years ago, Roshi said, leave off while the play is good. So having such motivation, I took my pleasure some 20 years ago to propose a new concept called game refinement theory, using analogy from Newton mechanics, in particular with focus on the acceleration, the second derivative in the sense of dynamics. So, what is the game refinement theory? The fundamental concept is the motion of objects is affected by gravity on Earth. Likewise, the motion of things or events like games is also affected by gravity.
But did you already start for the second slide or not? You have to push on the button for the next slide.
Can you see it?
We can only see the first page. It doesn't seem like you've advanced in the slideshow on our side.
This is the first.
Yes, we are still looking at the first page.
This one? This one?
It's still the first page. Sorry.
Still first page?
Yes.
Oh. I will try to upload again. I'm sorry. Yeah?
No worries.
I'm not sure which slide is better. I believe this one. Can you see this slide?
Yes, we can see it.
No, but that's the first one still. Yes, okay. Let me go also the previous one for having a look here. Yes. This is 40 years ago.
This is the second slide.
Yes, okay. But we would like to see.
Some 40 years ago, myself played the shogi. Left side. Yeah?
Yes,
this
okay.
Third slide. I'm talking for. Yeah? Okay. Yes. So what is game refinement theory? The fundamental concept is the motion of object is affected by gravity on Earth. Likewise, the motion of things or events, like games, is also affected by gravity, but this is a gravity in mind. The process of solving uncertainty of the game outcome is as if it were a free fall motion, namely uniformly accelerated motion. That's the idea of the game refinement theory. So here is a formula, xt equal 1 over 2 at square, where a equal gr square, game refinement measure, approximated by b over d square. B and D stands for average branching factor and game length respectively. The data in the table shows GR values of G's traditional board game, chess, shogi, and Go are almost the same, somewhere between 0.07 and 0.08, which we call GR zone value. It is well known these games are well sophisticated with long history, say more than 1,000 years. As the illustration, right side, shows, each stand on the gravity in mind curve or in the GR zone. In 2004, these findings was presented in the Entertainment Computing Conference, showing the popular board games, chess, shogi, Go, and mahjong are in the GR zone. Next slide. So here, actually, since that time, 2004, I've tried to apply the GR measure to many other types of game, or even in other domains such as business, education, etc., to observe how GR measure works in different areas. Here are several examples of how game refine measure works in different domains, such as soccer, baseball, tennis, basketball, tennis, baseball, boxing, and Pokemon. Having seen the history of sports games, their GR value moved to the GR zone. Sports games would be more exciting when its GR value is approaching to 0.08 or more. In Pokemon battle game, a trainer, Pokemon trainer can bring 6 Pokemons as default and takes the battle action against another trainer. A question came to my mind. Why 6 Pokemons? No changed since its first release by Nintendo. Why not 3 or 8? For example, using 4 different level AIs, we simulated and found 6 Pokemons are in the zone, GR zone for level AI, low level AI, which may correspond to novice player or little children. But for expert level AI, 4 Pokemons are in the GR zone. Indeed, actual regulation of Pokemon Battle Championship use 4 Pokemons instead of 6 Pokemons in the real human tournament. Anyway, not only in long history sophisticated mind sports like chess and go, but also in competitive sports games, we could see the GR zone plays an important role to be sophisticated or highly engaged. Here is another example. GR measure has been applied to observe the evolutionary changes of mind sports such as chess, go, and mahjong, where data were collected by self-play experiments using each AI. Each game shows somehow a different direction of evolution in the history, but came to GR zone eventually. Therefore, it is likely GR zone includes a border between fair and unfair, or competitiveness and non-competitiveness. This implies there is a link between fairness and competitiveness or engagement in games. So let's consider a link between board games and reinforcement schedule, in particular, variable ratio reinforcement schedule. In the simplified move selection model in board games, players narrow down the list of plausible candidates, say, from large B of all possible moves to small b of plausible candidate, as shown in this illustration, by skill at the first stage, and then randomly select a move to play among them. Why random? Because players are not perfect to always determine the best move. Thus, we recognize a board game becomes a stochastic game with fewer options, as shown in this illustration. In other words, any board game can be recognized a kind of variable ratio reinforcement schedule. The degree of reinforcement depends upon how often the reward is given, and VRN denotes the variable ratio reinforcement schedule with such frequency M. It is supposed in the reinforcement running domain that VR reinforcement schedule represent gambling or sports competitions like soccer. It is equivalent to receiving the reward with probability 1 over n. On the other hand, board games are also attributed to stochastic event with fewer possibilities when considering such move selection model. So here is an overview of a typical reinforcement schedule, which was proposed in 1957 by Skinner from Department of Psychology, Harvard University. There are mainly 4 types of schedules: fixed interval schedule, variable interval schedule, fixed ratio schedule and variable ratio schedules, as shown in this slide. So, Isaac Newton formulated gravitational theory in 1665 or 1660 after watching an apple falling down and asking himself why the apple fell straight down rather than sideways or even upward. Following the Newton's great work in the pandemic time in 17th century, at the time of COVID-19 pandemic a few years ago, I've tried to establish a gravity in mind theory as analogy of the law of universal gravitation in Newton mechanics. So, to summarize this introduction part, after first 30 years as a shogi player and the following 30 years as game AI researcher, I came to the concept gravity in mind based on the early work of game refinement theory, namely the motion of things like games is affected by the gravity in mind, as the motion of object is affected by the gravity on Earth. This implies two paradigm shifts. One is a transition from performance optimization to mind optimization to feel comfort in the AI context. Another paradigm shift is a transition from the motion of object by Newton in 17th century to motion of things just a few years ago. So now let me continue with some more detail of the gravity in mind theory as analogy of Newton mechanics. Since my own PhD time in early 1990s, my approach was, say, using games as an experimental testbed for AI research. For example, it was my interesting experience with my colleague to develop shogi AI named Tacos, and fortunately won the gold medal 4 times in the Computer Olympiad, as introduced by a chair of this session. In such project, I studied a lot of future possibilities, such as machine learning and other many AI advanced techniques. Actually, these AI-related ideas are mainstream in the current society, business, and government decision, etc. Thus, I changed my mind. Namely, I've been interested in more general theory of artificial intelligence, like Newton mechanics and universal gravitation. In this context, I have proposed a new concept, which I call gravity in mind. The concept of universal gravitation or just gravity was big findings or even fantastic hypothesis at that time in the history of science. It was done by Isaac Newton in 17th century, and together with the inverse square law, like this formula in the slide. In physics, the various physical formulations have been established around the motion of an object. The most fundamental of such formulation was the measure of the force, momentum, and potential energy. In this study, establishing those formulas in the game involves analogical links. This table shows such analogical connection between the physics model and the gameplay model. In the Newton mechanics, the velocity is defined as the rate of the change of displacement over the time, like dy over dt. A thing like game is characterized by its velocity, that is, the win rate or the rate of receiving the reward, namely VR reinforcement schedule. An object is characterized by its mass in newtons mechanics, whereas an agent is characterized by its intelligence. For example, higher intelligence would feel lower uncertainty in a given task. In essence, a stronger player has a higher skill to solve uncertainty in a given game. This situation implies the stronger player would meet lower uncertainty during a game. Thus, smaller value of mass, say M, is given to the stronger player. He might have understand novelty of creating a sophisticated game when Wilhelm Leibniz mentioned about game design by saying human beings are never more ingenious than in the invention of games. It is likely that design of sophisticated games is to implement the mechanism of the nature, like the law of motion. This situation would imply sophisticated games are eagerly played with great pleasure as a human experience becomes closer to nature. Our findings was a new concept, which we call gravity in mind, how it works in our mind. Let me show you an example using classical board game, say chess. Chess is a two-person game with average branching factor about 35 and game length 80 in master games. Our calculation to find the frequency n of variable ratio reinforcement schedule is around 5. It implies that y equal vt where velocity v equal 1 over 5 or 0.2. Moreover, our previous study shows game refinement indicator, which we denote GR zone, is somewhere between 0.07 and 0.08. The gravity in mind, say A, is given by GR square. Then the game of chess is influenced by the gravity in mind. So the game length should be approaching to the cross point between y1 and y2 in this illustration. Thus, we know the average game length of chess must be around 80 on average. This is because people, say chess players, follow their gravity in mind. In other words, the motion of things like chess is affected by gravity in mind of players. We observe the gravity in mind identify the border between objectivity and subjectivity in a given task, like gameplay. This is what I call minimal objectivity. Once the result of the thing under consideration becomes clearly predictable, the thing should be ended. Otherwise, the thing becomes boring while losing its entertaining. In shogi, it is done by the resignation. Losing player is responsible for maximizing the artistic value of the game by the most appropriate timing of the resignation. So game is characterized by its reward function with stochastic nature, namely frequency n of reinforcement variable ratio schedule, VRN. The length of game should be established under the influence of the gravity in mind, while satisfying y1 equal y2, where y1 equal vt and y2 equal 1 over 2 at square with a equal gr square. Using games as testbed, actual data from many different games show GR zone is located somewhere between 0.07 to 0.08. The gravity in mind corresponds to the cross point between y1 and y2, which is a border between fairness, meaning playing longer, and entertaining, meaning playing shorter, or between objectivity and subjectivity when the people make share of the game's outcome. Thus, gravity in mind finds the border between objectivity and subjectivity, which implies the most reasonable game lengths in the competitive context. Indeed, this can be applied to any competitive games as shown in this table, since the game outcome should be uncertain until the very end of the game in such type of games to enjoy more, otherwise feel boring and forgotten in the history of game. Here we see the velocity of both games can be approximated by a V equal 1 over 2 times B over D, with average branch factor B and game length D. This calculation comes from the approximation A, gravitational, gravity in mind A equal B over D square. Hence, its square root GR equal square root B over D. Y2 equal 1 over 2 AT square with A equal GR square, and Y1 equal VT with V equal 1 over 2 times B over D. When we apply the V value of chess, velocity of chess, the cross point is given by T0, Y0, where T0 equal AT and Y0 equal B over 2 equal, say, 17.5. Moreover, we can find the frequency n of VR reinforcement schedule, namely n equal 1 over V inverse. When n becomes larger, the target event is more stochastic. Likewise, when n is smaller, the event is deterministic or more skill depends in the game context. Interesting point is, for example, search space complexity of Go is much larger than chess, but chess is more stochastic than Go, since n value of chess is larger than Go. So let's consider from the creating point of view of a thing. A thing can be created in harmony with comfort and discomfort, which corresponds to the fusion or unifying gravity in mind and jerk in mind, the change of the acceleration. This is what I call Fushizen no myo in Japanese. We may feel comfort in the space with normal gravity, but discomfort with much larger gravity, like roller coaster experience. However, a harmonic combination of gravity in mind and jerk in mind produces a highly comfortable or even addictive thing. Gravity in mind provides exciting game experience based on the game outcome uncertainty. Jerk in mind, the change of gravitational acceleration can strengthen the engagement under the condition as shown in the illustration. We found the actual data support this hypothesis. This table, right side, that shows actual data from card game Fighting Around the Road, or Doji Zu in Chinese, which is the most popular card game in China, and it's a really addictive game on the internet. It is supposed that more than 1 billion people play this game online each night. We collected the data from many different regulations using AI. Among all such regulations, the best one in the sense of the most engaged is the case GR equal AD, and the cross point between Y2 gravity mind curve and Y3 jerk in the mind curve, green one. Y2 is a red one, Y3 is a green one in the illustration, which correspond to the gravitational acceleration and jerk in mind, respectively. Here, Y2 equal 1 over 2 AT square with A equal GR square, and Y3, the green one, is a 1 over 6 times J T power to 3 with J equal AD power to 3. Namely, AD is a cube root of jerk. Then a new thing is produced, which is a straight line, Y equal VT, blue color line. passing the cross point of y2 and y3. The illustration suggests the case where GR and AD equal AD would produce attractive game, which has game length around D equal 40 and branching factor B equal 10. Actually, Mahjong is one of such games. Thus, it is likely the gravity and jerk in mind meet at addictive zone in a given task. This would be fully established after some more investigations, and addictive mechanism will be more clearly understood. Addiction is somehow negative impression in game playing context, but important in other contexts such as learning, education, business, customer retention, and so on. So a roller coaster experience suggests that we feel comfort when we are in the space with normal gravity, say G equal 9.8 meter per second square. But we might feel discomfort when we are in the space with greater gravity like 5G. Our recent survey, as shown in this graph, left side, N equal 533 subject participated, shows that people would feel exciting and comfortable at 3G space, which might be a border between comfort and discomfort for many people. So we thus make analogical reasoning that comfort is given by the standard degree of gravity in mind, and discomfort is given by too high degree of gravity in mind or gravity of play by taking jerk in mind. Where is the border between gravity and jerk in mind to feel most exciting or even addictive? The magnitude of thrilling experience may be given by the ratio of gravity of play over the gravity in mind, A over A0. The acceleration, gravity in mind A stands for the gravity in mind, and A0 gravity of play produced by the jerk in mind. We obtain A over A0 equal square root N. So therefore, we reasoning when N equal frequency N equal 9, A0 over A over A0 equals 3. So this means YT equal VT with V equal 1 over 9. This shows a border between such efficiency skill like alpha-beta algorithm and evaluation skill. This is like a card game, for example, incomplete information games. That's the reason why incomplete information games like card games or in chess, Kriegspiel are usually so engaged. How we create or design new things such as game or other events. Any event should have a goal to achieve or reward to win. This implies such an event can be characterized by its velocity or the frequency n of VR reinforcement schedule. Then velocity is defined as V equal 1 over A n. In the motion of mind or motion of things, the concept of velocity is defined in this way. Here we have two curves. One is a red color with a normal gravity in mind, say y2 equal 1 over 2 at squared. Another one is a green color curve with jerk in mind, say y3 equal 1 over 6 jt power to 3. Solving the cross point between y2 and y3, we obtain t0, y0. Then we find the blue color straight line to pass the cross point, say y1 equal vt, where v equal y0 over t0. That's a new thing, which is characterized by its velocity, v equal n inverse, is created, which should be in harmony with comfort and discomfort in order to highly be attractive. By solving y2 equal y3, we find the solved information or certainty of the thing under consideration, say y equal 9 over 2 times a power to 3 over j squared. This implies the certainty or confidence of the result of the thing is proportional to gravity in mind a power to 3 and inverse proportional to jerk in mind j power square. In particular, the thing would be highly engaged or even addictive when GR equal AD. Here, phi denotes the GR over AD ratio. Hence, phi equal 1 when GR equal AD. This corresponds to the border between skill and chance in a given event. In case y equal 9 over 2 or 4.5, this information per event may be not enough to make sure more objective result of the event, or certainty is too small. That's why people need to repeat such things or need to play such games in order to obtain sufficient information or objectivity, like who is certainly stronger in the game rather than who wins a game. So now let's consider more stochastic event, which would be random reward event with large N or VR reinforcement schedule. As we see in board games and card games, say in all such competitive games, such event has small n value, relatively small, say less than n equal or less than 10. What happens if the event has larger n? Very large n may correspond to an event with very low win probability, like lottery. Here, we consider the gacha as a test bet, since gacha or gachapon is very popular in Japan. A question came to my mind: what N would be the best to enjoy the event? In other words, what is the essential factor of gacha to be so engaged? When N becomes so large, the event would be more stochastic. Then reward is given somehow randomly, meaning no skill works to win. So here, again, we have two curves. One is a red curve with a standard gravity in mind, y2. Another one is a green color curve with jerk in mind, say y3, r2, 3. Solving the cross point between y2 and y3, we obtain t23 and y23. Then we find the blue color straight line to pass the cross point, say y1 equal vt, where v equal y23 over t23. By solving y2 equal y3, we find the solved information or certainty of the thing right game, say y23 equal 9 over 2 times a power to 3 over j squared. Let's consider the ratio of full information, say yt over the information of the event per attempt, y23. Full information means the objective result of the thing under consideration. Now, yt over y23 would indicate how many times necessary to repeat the event to make sure the objective result of the event. As shown in the slide, when phi equal 1, y over y23 equal 2 power to 6 equal 64. This implies that the event with n equal 8 should be played so many times, like 64 times, to make sure the result. If phi is less than 1, player has to play more than 64 times to get confidence. Actually, when we assume GR equal 1 over 12, we estimate n approximated 2 over 5 power to 3. And hence y over y23 is estimated n squared. For example, if n equaled 50, people would play 2,500 times to feel objectivity. That's why people need to repeat some type of game so many times. namely being addictive, in order to obtain sufficient information or certainty. So here is an example from gacha. The magnitude of excitement experience is given by square root n. The minimal objectivity is given by the cross point y1, 2, meaning the cross point between y1 line and y2 gravity line curve. y1, 2 equal t over n in this graph, where t stands for the game length when n equal 1, meaning very objectivity. Solving the cross point between square root n and t over n, we obtain n equal t over t power 2 over 3. Assuming the GR zone event, for example, the case t equal 400, we obtain n equal 55. In the illustration, it corresponds to the cross point between red color and green color one. The cross point would be the peak of engagement as a border between skill and chance, necessity and randomness, or gaming and gambling, random reward. Actually, our data from gacha suggests the most popular gacha, Shingen Impact, on the internet has such value. So almost, since the value of the acceleration or gravity of play, A, can be regarded the measure of gravity in people's mind, it may serve as an indicator to the core culture of people of a specific era or time, as suggested by Huizinga in his well-known book, Homo Ludens. Hence, analyzing the change of the gravity of play, A, provides insight into people's cultural tendency based on their game playing experience and comfort. According to Merriam-Webster definition of game, one of the tacit meaning of the term is used in hunting, referring to wild animals hunted for sport or food. Based on the historical development of Go game, the reduction of gravity of play, A, demonstrates the transition of people from nomadic culture, hunter-gatherer, into sedentary culture, agriculture, where people search for a more stable lifestyle. Suppose the N is approximated as a day with a reward a year, then the hunting process is equivalent with reward requiring short-term work. Say N is in the 50 to within the 50 to 100. N is in the range of the 50 to 100. While agriculture, for example, crops like wheat and rice requires long-term work. For example, N is in the range 150 to 200, for example. Another direction of history is a transition from agriculture to a more exciting lifestyle, leading to the Industrial Revolution and free capitalism, where gravity of play, A, increases and N decreases, meaning more skill-based or competitive. Such historical development is related to the chess game, where war, conquest, strategy, and tactics played an essential role in early people's lifestyle. The people's culture then shifted toward capitalism, efficient transition, such as horse-powered transport and railroad and voluntary goods trading, and industrialization, mass production, and machinery usage allowed more frequent reward gains with medium to short-term work from, say, N equal 200 into N equal 100. The third phase of the evolution of Mahjong is the period of transition in history, where both the gravity of play, A, increases further and decreases again, N decreases and increases. Such historical development implies changes in the people's culture toward fast-paced and highly accessible goods, fair invention such as mechanization since 13th century and computing devices in early 19th century. and modernization, first and second industrial revolutions. With such changes, the reward frequency significantly improved, n equals 30, around 30, and stabilized with an increase of urbanization, say n equals 50, something right. Based on historical development of gravity of play, A, for the board games along the period of the development as shown in this figure, a symmetric-like trend was observed, bordering at about 4th to 5th century. Such a trend overlaps between the Go and chess games development, where as showed opposing trends between Go and chess. Such a symmetric border implies the turning point of the game's development, which is demonstrated by the first phase and the second phase of the game's evolution. It would also represent the border between competitive and mastery activities. Anyway, the research in this direction would be interesting to go further. So, concluding remarks. Here are some concluding remarks in the 4 items listed here. I would here emphasize the last item. AI with gravity in mind would be important next milestone. Then AI will be able to identify the best timing for resignation, by which AI could become a wonderful athlete as well as fantastic artist. The things are in harmony with comfort and discomfort. The peak of addictive things will be seen when satisfying GR equal AD. That is the square root of the acceleration, say A equal GR square, and the cube root of the jerk, say J equal AD power to 3. It corresponds to the border between skill and chance, or between necessity and randomness in the things under consideration. So, in our life as a game, comfort alone is not enough for growth. In many ways, it is essential to experience adversity or challenge and find your own way to maintain the balance, namely maximize your curiosity in life. That's Fushizen no Myo in Japanese I mentioned in this talk. Here are a list of selected publications since my 2020 paper on this topic, the motion in mind, based on the gravity in mind concept. My big thanks to PhD students in my lab who worked so hard to realize the paradigm shift from the motion of object to the motion of things like games. So at the very end of my talk, let me introduce one paragraph, one sentence by Albert Einstein when he used to explain his gravity theory and relativity concept, saying, gravitation cannot be held responsible for the people falling in love. But I would say gravitation in mind can be held responsible for the people falling in love. That's why many old students from my lab enjoy their lives with their partners, wife and husband, with their children like this photo. Thank you. Thank you for your attention. That's it.
Okay, thank you.
Thank you so much. Questions? So for people who have not been here yesterday, please try to ask the questions in the Q&A section. And if you're a panelist, feel free to ask in the chat because the Q&A can only be inputted by non-panelists.
Should I stop this upload by file slide? Or still
it's probably nice to keep it in case someone asks questions about something within the talk itself.
Okay.
Thank you. Yeah.
I will keep it. I'll keep it.
It's a lovely page. I really like this page.
You like it? Okay.
Yes, it's wonderful. Yeah. So maybe I can ask a guiding question just to, start the process. I was wondering about the parts where you mentioned about games being addictive. I imagine that, some of these modern games that are designed purely to, elicit some kind of reaction from players so they can engage longer and play more and earn the company more money. In some ways, it is actually kind of predatory and can be dangerous. I was wondering what your thoughts on that would be in terms of, the emotions of the mind.
What do you expect? My answer. It's
I wonder, since
trend of
you've
the game.
yeah, since you've done research on this area and that there might be ways to measure this kind of addictiveness, for example, which is
Right.
previously
Well,
unquantifiable, right?
No person who tried in this direction. That's why I tried.
I find
It's
it
not,
very intriguing, so I wonder what your thoughts on that would be.
yeah, actually, one of the good inspiration come from the Leibniz. My
Hmm.
interpretation of the Leibniz word is like we need to understand the mechanism of the nature. After long, careful thinking of this word, my conclusion, is something like the gravity on Earth. When we stay with in the space with normal gravity, standard gravity, G equal 9.8, yeah, we
Hmm.
feel comfort,
Hmm.
very natural, very natural. But if you take like a roller coaster, 5G or 6G, 7G, yeah,
Hmm.
cannot feel comfortable, discomfort.
Hmm.
But in some sense of the context of the entertaining, 3G is still can enjoy it.
Right. There are like acceptable levels of excitement is I guess
Right,
another way to
right,
put
right,
it.
right. A kind
Yes.
of between the border between safety and risky. Such a border is very important to enjoy, increase more or maximize something. That's the idea.
I see. A few questions are coming in. Thank you for your intriguing presentation. One question, you can say gravity on Earth, on Mars, on dot dot dot. What about gravity in the mind, depending on, different people in the minds of, say a person X or some other person Y?
Is a chat?
Yes, in the chat.
Okay. Gravity on Earth, on Mars. Oh, what about gravity in mind? Depending on persons. Aha. Yes, we should consider such individual different, but I believe almost similar, like in the a survey in the roller coaster, because many people around like 50% people like 3G, but other 50 people percent people like other case lower or higher. So therefore, we should consider such individual difference.
Mhm.
But that's why we consider the GR zone value, not 0.07 or 0.8 zone.
Right, there's a range. I see.
Right. Range,
Yes.
yes. Right.
Another question in the Q&A. How is gravity in mind defined exactly? What is its value for shogi, go, and chess?
How is gravity in mind defined exactly? What is its value for shogi and go and chess? Yes. Gravity in mind is like a standard one. Every sophisticated game should stand on the gravity in mind curve, but each game is a different velocity. So meaning a different, the gravity of play. is produced by a jerk in mind. This is what I explained it. So answer to this question, shogi, go, and chess has different velocity. It's meaning different frequency and of how I say variable or ratio reinforcement schedule. That's the answer to this question. So this means a gravity of play is different, but gravity in mind is the same. Just in the gravity GR zone. So therefore, like the difference in the roller coaster case, a chess, go, and shogi has a different, I would say, magnitude of the excitement. Even though they are the same, stand on the gravity in mind curve.
Okay.
That's the idea.
Thank you. There's a series of questions from Yap. What is the border of gravity in mind? Can your mind cross this border, and what happens then?
Subjective excitement, but cannot be measured. Objectivity, but cannot be observed.
Oh, that's another question. Yes.
Objectivity means, in the sense of the reinforcement schedule, it's n equal 1, frequency n equal 1. Once you conduct something, you always receive reward. That's n equal 1. That's be the objectivity. That's a definition. That's a measurement. Is that the answer to this question?
Dimitri, does that answer your question?
I understand excitement is like emotion is basically subjective. But if you use discussion with how I say a reinforcement schedule idea, we could discuss such a objectivity and subjectivity based on the value of n frequency. That's one of the idea in this discussion.
I sent you some questions, but I'm not sure whether they came over.
They were part of the answer to a previous question. So maybe you can ask orally. I think if you can ask verbally, it might be better. Yes.
Yes.
Please go ahead.
Hiroyuki, you also spoke about necessity and chance, yes? That I understand. But my question is, you showed a graph, and that was a relation between the two, necessity and chance. But is there also a relation with playing strength?
Oh, playing strength issue. That's an important issue. Yes.
Yes.
As I mentioned at the beginning of the talk, for the strong player, uncertainty is not so much if you compare the weaker player. So therefore, it's important to consider such a level of players. Actually, in the next stage of the motion in mind theory, we use such a measurement with considering the level of player. That's also part of the motion in mind theory. At this time, I have no time to explain such detail. That's why I'm sorry I skipped this part. We should consider such a level of player. For example, V0 is like a perfect player. Then V1, V2, V3, something like the parameter represent such a player's level. Then we can discuss more general. For example, in the game theory discussion, only focus on the perfect player, V0. But actually, we cannot have such a perfect player. So therefore, rather, we should consider VK or K2 or V3, K3 or something like that. I think it's a good.
Thank you. I have a second question also, and it coincides with your concluding remarks on the emotion of objects and emotional things. Yes, that I understand. But there's also what you said. Also, apart from emotional mind, you have also emotional mind. Yes, and what is the relation between motion and all the things you measured, and emotion. Let's say Huizinga was a person who involved emotion in his book, Homo Ludens. And already the title said so, but that is a very difficult part. And what is your idea on that? So the relation between emotion and motion of thoughts.
I think it's a very essential question. Thank you, Yap. Actually, I'm not saying about the emotion things, just the player experience. But of course, it's kind of the emotional. I understand. So gravity in mind is given influence to the player's behavior with
Yes.
some emotion. But
Yes.
I'm not saying about the emotion, just the influence. The
Yes, I
output
understand.
of the game
But
ranks or something like in game context.
as a showbiz player, you know very well that apart from gravity of motion, yeah, there is also an important point of gravity of, I would say, emotional feelings, because they are very important for your, I would say, performance.
Right. That's be the next stage to discuss more detail of the emotional aspect based on this kind of discussion.
Okay, then I want to strengthen many PhD students with this next topic.
Right. Unfortunately, I'm all nearly retired from the professor.
Yes, I understand. But anyway, because also I in fact you advocate in one of your slides that you should publish that in the ICCA journal. But I have not seen anything about this topic in the ICCA journal recently.
Yeah,
I'm
I'm
not
very
anymore
sorry.
the editor that I know, but anyway, we have 3 editors now, and I would say that I could encourage them to invite you to publish there some of your findings.
Right. I should publish in the ICG journal. I'm sorry.
Okay, thank you.
Thank
And
you.
I say, by the way, it was a great talk. So I listened with much pleasure, and I learned also a few things out of it because I thought, oh yes, that's a connection. So thank you for inspiring me and encouraging me to, I would say, to think further on this topic. Well done.
Thank you. My pleasure. It's up to you. Yep.
Okay.
Thank you very much. It was my pleasure.
Thank you, Professor Iida, for the talk. We're coming up on the time, and I don't think there are any more questions. So maybe we can call it. And I'm not quite sure how long the break is until the next session. But yes, thank you very much for the wonderful talk.
Thank you. Yeah,
very interesting.
Thank you.